Hello everyone, welcome to my 16th video lecture on infinite series. In this video, we shall discuss about absolute and conditional convergence of the given alternating series. Now let us define what is meant by an absolute convergence of the given alternating series. If we are given with an alternating series, which we usually denote in the symbolic form as minus 1 to the power n minus 1 into un. So the meaning of this we have already seen that it is u1 positive sign minus u2 plus u3. So alternatively positive and negative signs will be appearing in the given alternating series. That will be accounted by this particular factor in the notation. Now this is the given alternating series. On this alternating series, if we do something, that is what we need to do. We need to consider each term of the alternating series as a positive term. That is what we are going to consider. We are going to consider the absolute of each term. Absolute of each term involved in the given alternating series if we consider. So the meaning is that we have to make each term positive. So here we are observing u2 is with negative sign, it should be made positive. u3 is positive, it will remain as positive. u4 is with negative, it will become positive u4, like that. So it will become the simple series of positive terms, that is summation un. So therefore now with the alternating series in hand, we obtained a new series in which all the terms are made positive. Now we shall check the convergence of this. So if the given if the series so obtained, that is the absolute series, we can say it as, if this absolute series is convergent, then we say that the given alternating series is absolutely convergent. That is if summation un, which is the absolute series, I will write here. So I have made all the terms in the given alternating series as positive and obtained this new series and called it as absolute series. If this series is convergent, then the given alternating series, that is denoted as minus 1 to the power n minus 1 into un, this is of course we know it is an alternating series. If this is convergent, then this given alternating series is said to be absolutely convergent. So this is how we can define the absolute convergence of the given alternating series. So the meaning is that when the series, that is the alternating series given to us, is absolutely convergent, it means that the given series will be definitely convergent. This we have to take it in the form of a note. That is straightforward, because absolutely convergence, an alternating series is absolutely convergent if the absolute series is convergent. So the meaning of this is that the absolute series, when it is convergent, there is one important remark we considered in the beginning itself, that when a series is convergent, then even if we make some of the terms in that as negative, then also the series will remain as convergent. Therefore the alternating series is so obtained by making the alternative terms of this series positive and negative. So therefore if this is convergent, then the series obtained from this by taking alternative positive and negative signs, that is an alternating series, will also be convergent. So therefore the absolute convergence always imply the convergence of the given alternating series. Here we have to distinguish between absolute convergence of the alternating series and convergence of the alternating series. So absolute convergence is the strongest property we can say, because when the given alternating series is absolutely convergent, then we say that it is convergent. But it is not necessarily true in the reverse direction. That is, we cannot say that if the given alternating series is convergent, that we check by Leibniz test, if it is simply convergent, the given alternating series, then we cannot conclude that it is absolutely convergent. So this is an important thing, and this gives us another important definition, and that is known as the conditional convergence. So conditional convergence, what it is? The given alternating series is said to be conditionally convergent if, so what we are considering, the given alternating series minus 1 to the power n minus 1 into un is conditionally convergent if it is convergent, this series is convergent but not absolutely convergent. That is, when the given alternating series is simply convergent as per the Leibniz test, but it is not absolutely convergent. In that case, the series, that is the alternating series, will be called as the conditional convergent sequence. So this is how we have defined the absolute convergence and conditional convergence of the given alternating series. Let us solve some of examples on this. Let us consider the first example where we need to test the given series, that is, this is the given series. For the first question is for convergence, second question is for absolute convergence, and the third question is for conditional convergence. We have to check the given series for these three things. So let us solve the example. So first of all, we shall consider the given series in the symbolic form. So what is the given series? It is summation minus 1 to the power n minus 1 into un. This is the symbolic form of an alternating series. So that can be written in this particular case as summation minus 1 to the power n minus 1 into, in place of un, we have to generate the terms. So the first term is 1 divided by 1. The second term is 1 divided by 4. So this 4 can be written in terms of 2 as it is 3 into 2 minus 2. That is 6 minus 2. We can observe here, this is 6 minus 2. This is 8 minus 2. Sorry, this is 9 minus 2, 6 minus 2, 9 minus 2, 12 minus 2. So therefore, and even this is 3 minus 2. 1 by 1 it is actually. So it is 1 by 1 means it is 3 minus 2, it is 6 minus 2, it is 9 minus 2, it is 12 minus 2. So each one is a multiple of 3 minus 2. So therefore the nth term will be 1 divided by 3n minus 2. So this is the nth term we have generated so easily in this case by looking at these terms. Now this implies, so here what is un? Of course it is 1 divided by 3n minus 2. Now we have to solve the problem. First, the first question is to check the convergence. In order to check the convergence, we shall use the so-called Leibniz test. So in the Leibniz test, we have to have un plus 1 along with un. So what is un plus 1? Un plus 1 is obtained by simply replacing n by n plus 1 in un. So it is 3 into bracket n plus 1 minus 2. So it is, after simplification, going to be 1 divided by 3n plus 3 minus 2. It is going to be 3n plus 1. Now we have to check the first condition of Leibniz test. What is that? Un must be greater than un plus 1. Therefore we have to consider un minus un plus 1. So if we consider this, what is the answer? We shall check it out. So it is un, we are writing here 3n minus 2 first, minus sign, un plus 1, it is there, it is 3n plus 1. So we have to take the LCM. When we take the LCM, LCM is going to be 3n minus 2 into bracket 3n plus 1. So these are the two factors coming in the LCM. So here with this one, 3n plus 1 will be multiplied, minus sign as it is. With this one, this 3n minus 2 will be multiplied. 3n minus 2 will be multiplied. Now after simplification, 3n minus 3n cancelled. 1 minus minus plus, it is 2. 1 plus 2 is 3. So it is a positive quantity we obtained here. And in the denominator, it is 3n minus 2 into 3n plus 1. So we observe that for n equal to 1, it is 3 minus 2, it is going to give us positive quantity. For n equal to 2, 6 minus 2, that is 4. Surely it is positive quantity. For every n, these terms, this term, they are going to become positive. And this is already positive. So this entire thing is positive for every n. So what we have proved, this implies that un minus un plus 1 is a positive quantity for every n. So this implies un is greater than un plus 1 for every n. So this is the first condition satisfied. The first condition of Leibniz test is satisfied. Now the second condition we are considering. So that is limit of un we have to check for n tending towards infinity. So that is equal to limit as n tending towards infinity of, what is un? Un is 1 divided by 3n minus 2. So when we substitute n equal to infinity here, so it is going to be 1 by infinity, that is of course 0. So therefore even the second condition is satisfied. Therefore by Leibniz test, given alternating series is convergent. So the first question is, the first part of the question is over. Now to check the absolute convergence of the given alternating series, we have to write the absolute series. The absolute series we can write down from the given alternating series. The given alternating series is 1 minus 1 by 4 plus 1 by 7, like that it was. And we got the general form as minus 1 to the power n minus 1 into 1 divided by 3n minus 2. So in this we have to consider this to be positive. So therefore summation of 1 divided by 3n minus 2. So when we take absolute, this minus sign will be disappearing, only the quantity will become positive. So this thing remains, and this is our summation un, and therefore it implies un here is 1 divided by 3n minus 2. So in order to check the absolute convergence, we have written the absolute series, that is absolute series is this thing, and from that we got the value of un. Now we will discuss the nature of this particular series. So whether it is going to be convergent or not. To check the convergence of absolute series, that is summation un, we will consider one of the tests which we have already discussed. So in this case un is very simple, 1 divided by 3n minus 2. So we can simplify this by taking n outside here in the denominator. If we take n outside, here remains 3 minus here remains, it is 2 by n. So let us take this 1 by n as Vn, where Vn is 1 by n we have taken it as. So by taking Vn equal to 1 by n, it is Vn remaining here, and the remaining thing is 1 divided by 3 minus of 2 by n. Now if we transfer this un to this side, it will become un by Vn equals to 1 divided by 3 minus 2 by n. Now let us take limit on both sides. So what is the guess here? Which test we are applying? We are applying the comparison test in the limit form. That is the third type of comparison test we are applying. So therefore we are advised to take limit as n tending towards infinity of un divided by Vn, and that is going to be limit as n tending towards infinity of 1 divided by 3 minus 2 by n. So this answer is 1 divided by 3 minus 2 by infinity is 0. So it is 1 by 3. So when the limit is not 0, then we can conclude that by the so-called comparison test. Therefore by comparison test, the two series, one is summation un, that is of our interest, and the new series which we have generated right now, that is summation vn, behave alike. That is their nature is same. Since summation vn is what? Summation of 1 by n. We have taken 1 by n as vn, therefore summation vn is nothing but summation of 1 by n is what type of series? Is a p series with p equals to 1. It implies that when p is equal to 1, when p is less than or equal to 1, the p series is divergent. Therefore summation vn is divergent. When summation vn is divergent, it implies that summation un is also divergent. So what we have proved? We have proved that the absolute series, that is the absolute series is divergent. When the absolute series is divergent, it implies that given alternating series is not absolutely convergent. This is our conclusion here for the second part of the question. So what we are considering, the given, what we are concluding here, given alternating series is not absolutely convergent. That is our derivation, that is our proof. And now we shall move on to the third part of the question. So the third part of the question is to see whether the given series is conditionally convergent or not. So it is the conditional convergence we are checking for. So from the first part, given alternating series is convergent, and from the second part of the solution, given alternating series is not absolutely convergent. So we have in hand the definition of conditional convergence is that it is an alternating series which is convergent but not absolutely convergent. But the series which we are having in our hand now is convergent, but it is not absolutely convergent. Hence given alternating series conditionally convergent. So this is our conclusion at the end. So this completes the solution of the first problem.